zero resultant of a triangle. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lesson, we explored the triangle law of vector addition. As you recall, that principle was fundamental in teaching us how to calculate the resultant displacement. Essentially, how to find the single net vector that represents moving from one specific point to another. Now, today we are going to build on that foundation by examining a very specific and interesting special case. We are going to look at what happens to our vectors when a path doesn't just move from point A to point B, but actually forms a closed loop, specifically a triangle, where the journey eventually leads you right back to your original starting point. Let's see how this affects our final result. Understanding the concept. Think of it this way. Whenever we add vectors together, we are essentially tracking a journey. We start at an initial point, move through various displacements, and end up at a terminal point. Now, here is the crucial part to keep in mind for our upcoming derivation. If a particle starts at a specific point, moves along several different paths, but eventually manages to return to that exact same starting point, what happens to the net displacement? Well, the net displacement is zero. There is no change in the overall position from start to finish. Let's apply this specifically to the geometry of a triangle. Imagine a triangle with vertices labeled A, B, and C if we traverse the sides of this triangle in a continuous, sequential order, meaning we follow the perimeter from A to B, then B to C, and finally C back to A, we have completed a loop. Because we have returned to exactly where we began, we are setting the stage to prove that the sum of these specific vectors will result in a zero vector, which we will mathematically demonstrate in the next slide. Now that we've recalled the triangle law of vector addition from our previous slide, let's dive deeper into the core concept here. Step-by-step mathematical derivation. In step 1, let's look at the first two movements. Imagine a particle moving from point A to point B, and then continuing from point B to point C if we apply the triangle law of vector addition, which we studied in our previous lesson. The resultant displacement is simply the vector from our original starting point, A, to our new endpoint. C. In mathematical terms, we write this as vector AB plus vector BC equals vector AC. Moving on to step 2, we consider the return journey. To complete the loop, suppose the particle moves from point C all the way back to the starting point. A. This specific movement is represented by the vector CA. This brings us to step 3, where we need to relate vector AC and vector CA in vector algebra. If a vector has the same magnitude but points in the exact opposite direction, we call it the negative of that vector. Therefore, vector CA is the negative of vector AC, which can also be written as vector CA equals negative vector AC, or alternatively, vector AC equals negative vector C. Finally, in step 4, we perform the final summation to see the total result. If we add this return journey, vector CA, to our previous resultant, vector AC, we get the equation. Vector AB plus vector BC plus vector CA equals vector AC plus vector CA. Now, look closely at the right side of that equation. Since the particle has returned to its original position, the path from A to C and then back to A is essentially a movement from A to A. This results in the zero vector, which we denote with a bold 0. So, we can conclude that vector AB plus vector BC plus vector CA equals vector AA, which equals the zero vector. Now that we understand the concept of returning to a starting point, let's walk through the mathematical derivation step by step to see how this works on paper. As you'll see in the next slide, this isn't just abstract math. It's exactly what happens when a hiker completes a loop back to their base camp. Real-world example, the hiker's loop. Now, to make this mathematical concept a bit more concrete, let's step away from the abstract symbols for a moment and look at a real-world example, the hiker's loop. Imagine a hiker in a forest who is planning a trek to explore a triangular area with the ultimate goal of returning safely to their base camp. Let's break down this scenario step by step. First, the hiker starts their journey at base camp which we will call point A, and walks to a lookout tower, which we'll label point B in vector terms, this displacement is represented by the vector from A to B. Next, from that lookout tower at point B, the hiker continues their trek to a beautiful waterfall, which we'll call point C. This movement is represented by the vector from B to C. Finally, to complete the loop, the hiker walks from the waterfall at point C all the way back to the original base camp. At point A, this final leg of the journey is the vector from C to A. Now, let's look at the breakdown of the resultant displacement to see how this connects to the derivation we just saw in the previous slide. In step 1, if we look only at the first 2 legs of the trip, from the camp to the tower, and then from the tower to the waterfall, the total displacement from the camp to the waterfall is the vector from A to C. Mathematically, we say vector AB plus vector BC equals vector AC. In step 2, we add that final leg. The hiker takes the path represented by the vector from C to A to return home. By step 3, because the hiker has successfully returned to their exact starting point, the total displacement for the entire trip, which is the sum of vector AB plus vector BC plus vector CA, is equal to the 0 vector. It is important to note a key distinction here. Even though the hiker has walked a significant physical distance, specifically the entire perimeter of the triangle, their net change in position, or their total displacement, is exactly 0. This perfectly illustrates the principle we are about to summarize in our key takeaways. Key takeaways. First, let's talk about the concept of a closed loop. This is the most important principle here. Whenever you have a sequence of vectors that forms a closed polygon, just like the triangle we've been studying, and you add those vectors in a continuous, sequential order, their sum will always result in the 0 vector. However, there is one crucial condition you must remember for this to work. For the sum to be exactly 0, the terminal point, or the head, of the very last vector must coincide exactly with the initial point, or the tail, of the first vector. In other words, you must end up exactly where you started. To summarize this mathematically, we can look at this identity. Vector AB plus vector BC plus vector CA equals the 0 vector. Now that we have worked through the mathematical derivation and seen how this applies to our hiker's journey, let's consolidate everything we have learned with some key takeaways. As we move to our final slide, I want to highlight some common pitfalls where students often lose marks, particularly regarding the order of vertices and the difference between distance and displacement. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even when you understand the concept of a 0 resultant, it is very easy to make small errors that can lead to incorrect answers in your exams. First, let's talk about ignoring the order of vertices. This is a very frequent mistake. Remember, for the sum to be 0, the vectors must follow a continuous, unbroken path. You cannot simply pick any 3 sides of the triangle and add them. For example, if you try to add vector AB plus vector BC plus vector AC, you will find that this does not equal the 0 vector. Why? Because you haven't completed the loop. To get that 0 resultant we discussed earlier, the vectors must be placed, head to tail. Meaning the end of one vector must be the start of the next, like moving from A to B, then B to C, and finally C back to A. Second, be careful not to confuse distance with displacement. This is a conceptual trap. Think back to our hiker example from the previous slide. The hiker walked a certain total distance, which is the sum of the lengths of all the sides of the triangle. That distance is a positive scalar value. However, the resultant displacement, the net change in position, is the 0 vector. Don't let the physical effort of the journey trick you into thinking the displacement is anything other than 0 when you return to your starting point. Finally, watch your notation closely. In vector algebra, precision is everything. You must distinguish between the scalar number 0 and the 0 vector, which we denote with a small circle over the 0. While they both represent a lack of quantity, the 0 vector is a specific mathematical object that has a magnitude of 0 and an undefined direction. Remember, When you are adding vectors together, your final answer must always be a vector, not just a simple number. Keep these points in mind, and you'll avoid the most common mistakes in vector addition.